This week we will talk about forecasting. Forecasting is a predictive analytics technique used to reduce uncertainty about decisions in the future. Some examples of forecasts might be inventory needed to meet future demands, or how many patients we expect to see in the hospital on a certain day of the week or at a certain time of day. We're going to talk about both qualitative and quantitative methods of forecasting. While some managers may use years of experience and intuition to make forecasts, we're going to talk about several other more objective methods. Here we can break down forecasting into several categories. On the left, we have qualitative models, which we tend to use if we lack historical quantitative data. However, if we have quantitative data, then we will use either time series methods or causal methods like regression, which we learned about last week. Incorporate judgmental or subjective factors. They are useful when subjective factors are important or accurate historical quantitative data is difficult to obtain. The Delphi method is an iterative group process where a group of experts makes a forecast that respondents then critique, and this cycle repeats until a consensus is made, where the jury of executive opinion is just that, a small group of experts that make a forecast. The Salesforce composite is more of a bottom-up approach, where each salesperson makes a forecast, then the forecasts are reviewed at a higher level and move up to different levels of the company, from director to manager, all the way up until you get to the national level, and then that'll be your forecast. And finally, the one you're probably most familiar with are consumer market surveys. This method surveys consumers about the likelihood they will buy a particular product. There are many consumer reports on things like cars and about 5,000 other products through a company called Consumer Reports. The next set of models are time series models. Here, we try to predict the future based on historical data on one variable. This method ignores external factors. There are four possible components to a time series, including trend, seasonal, cyclical, and random. Trend involves a general up or down movement of data. Over a period of time. Seasonal effects are apparent when certain times of year create a pattern, like higher sales in the last quarter of the year. If we have patterns that tend to repeat every several years, we call this cyclical effects, generally stemming from longer-term patterns, like in the commodities market, the relationship of feeder cattle and live cattle. Feeder cattle are on a 2-year cycle and live cattle are on a 5-year cycle. Understanding these cycles can create money-making opportunities. The last component of a time series is associated with random effects, which are unpredictable and add variation to our forecast. Here we can visualize the effects of each of the components of a time series. Going from bottom to top, we start with Series 1, which shows a relatively flat amount of cells with mild variations, or random variations. In Series 2, we can see the effects of seasonality, where sales peak in the second quarter of the year. In Series 3, the sales are trending up, but still shows some random variation. And in Series 4, we can see the combined effects of seasonal, trend, and random components. This will lead to a more difficulty in forecasting accurately. How the different combinations of a time series work together can be both additive, multiplicative, or can use combinations of both. We'll talk about a few examples in a few slides. It is important to keep track of the accuracy of our forecasts. That way we can adjust them for improvements. There are several metrics for forecast accuracy. The first of which we will talk about is called the mean absolute deviation, or MAD. To calculate MAD, we sum together each of our forecast errors and divide by the number of forecasts we made. Let's do a quick example. Here we have a set of data on speaker sales. In the first column we have the actual sales, and in the second column we have our forecasts. Now this is a very simple forecast called a naive forecast, where our forecast is just the actual sales of the previous month. We are not adjusting for the time series components. To calculate the MAD, we take our actual sales and subtract our forecasted sale from each other, giving us the deviation. That's where we create that last column. We sum all of the deviations together and divide by the number of forecasts we made. We only count the number of forecasts that we have complete data on. So we do not have a forecast for the first year, and we do not know the actual sales of the 11th year. Thus we have 9 forecast deviations we can calculate on. There are other ways we can measure forecast accuracy, including mean square error, like with what we did in regression analysis. The MSE is the error squared, once again, to ensure we do not have positive and negative cancellations. We'll probably need to calculate this on a test. Mean absolute percent error allows us to look at forecasts with percentages, and bias is just the average error, and tells us whether our forecast tends to be too low or too high. For random variations, we can use moving averages. If our demand is relatively steady, then average the last few periods of time's actual sales and we should get a pretty accurate forecast. This will smooth out some of the short-term randomness. It is pretty simple. If you have a 2-month simple moving average, then you average the last 2 months' actual sales and divide by 2. This is your forecast for the next month. If you want to do a 3-month simple moving average, then you average the sales of the last 3 months, and that is your forecast for the next month. Here is an example. Wallace Garden Sheds has collected a year's worth of data. They are going to use a 3-month moving average to predict the number of sheds sold for next month. Wallace Garden Sheds wants to know what the next January's demand will be. They take the average of actual shed sales from October, November, and December and find an expectation of 16 sheds in January. This is an example of just a simple moving average. And the ability to add weight to a more recent month, and useful if a trend is emerging. With a weighted 3-month moving average, we need to multiply the weights by each of our actual sales demands and then divide by the sum of the weights. Here, we have a weight of 3 for last month, a weight of 2 for 2 months ago, and a weight of 1 for 3 months ago. Once we multiply those out times our actual demands, we have to divide by 6 because that is the sum of 3 plus 2 plus 1. And that balances out our average. So, in this example, we weight the previous month the highest with a weight of 3, then 2 months ago with a weight of 2, and 1 month ago with the weight of 1. We then divide by 6 because that is the sum of the weights. We can see in this example that our forecast is slightly lower than the simple moving average, but this is not always the case. To find out which of our forecasts tends to be more accurate, we could calculate the MAD for the simple moving average and the MAD for weighted moving average, and then select the method with the lower MAD. Smoothing is a form of moving average we use if we have poor record keeping or limited data. we select an alpha coefficient that we can smooth out fluctuation between the time periods. If we select an alpha of 0.1, then we will account for very little variation, and as we increase the alpha, we will see more effect. At 0.5, we have adjusted the forecast to account for roughly the last 3 periods. The new estimate includes the old estimate plus some fraction of error from the last estimate. Our goal is to select the alpha coefficient that minimizes our MAD value, or minimizes error in our forecast. Here is an example that compares using an alpha coefficient of 0.1 and 0.5. We calculate our forecasts. The MAD values, we can see that the alpha value of 0.1 produces a lower value of MAD than the alpha value of 0.5. Thus, we should use the alpha value of 0.1 for our forecasts, because it is more accurate. For random components of forecasting, we can use moving averages, but for trend components, we want to use regression. For regression, we have our typical slope-intercept form of a fitted regression line, and we can plug in values for the different variables in order to get our forecast for y. If we have our forecast equation, all we have to do is plug in our values. Here we have coded 8 as the year 2014. We plug in 8 for our x value and solve to obtain our forecast value. If we iterate to the next year, we can continue getting future years projected. Our regression line, our historical data, and then the 3 x's are our projected demands by plugging in the different coded time periods. And that is how we can use regression to forecast much further out, but typically the further out we project, the less accurate our forecast will be.